Okay, so now let's take another look at this piece right here. We said, well, okay, what use would any of this be? Well, what we're trying to do is we're trying to find out that there's some relationship between two quantities that we could actually use to help us determine a rate of change of two related quantities. And a real good example comes from this one. Let's say that we assume that oil is spilled from a ruptured tanker and spreads in a circular pattern. We're just going to assume it's a perfectly circular pattern. I know it usually isn't, but let's assume that it is. And the radius is increasing at a constant rate of 2 feet per second. The question might be, how fast is the area of this spill increasing when the radius is exactly 60 feet? So, all right, we've got this situation right here. Our oil spill is at 60 feet, the edge of it, right? 60 feet away from the tanker and spreading. And we know how fast it's spreading, right? Our radius right here is uh, at this radius is at 60 feet, and our rate of change of that radius is a nice steady 2 feet per second. Right, so we know at 2 feet per second that the edge of that spill is just drifting outward. So what we'd want to know is, what is the rate of change of the area? You know, how fast is the area increasing? So what we need is a relationship between the area and the radius. And well, ready made for us, right, is area is pi times r squared. And so we want to find the rate at which the area changes. We're going to call that dA dt. And we know the rate at which the radius changes. That's dr dt. So how do we set it up? In this case, what we're going to do, let's just start with our area relationship. Area is equal to pi times the square of the radius r. So we're going to take the derivative with respect to time of both sides, just like in our last example. So we take our derivative of area with respect to time and set that equal to the derivative with respect to time of pi times r squared. So what's going to happen right here? Well, area is a function of time, and we know that what's going to happen is if I take the derivative of area with respect to time, I just get dA dt. Well, that's what I want, fine, right? dA dt. How about on the right? Well, on the right, it's a little bit different, right? Because we've got this pi and r squared. Well, pi is a constant, right? So we're just going to leave pi out of this. And we'd be taking the derivative with respect to time of the quantity r squared. Now, again, r is a function of time. So in this case, we have to use the idea that we learned about in the chain rule right here, which is to say that since our variable that we're taking the derivative with respect to does not match the variable that we're taking the derivative of, we have to use our chain rule. So the derivative we know of r squared would be 2r, or 2r to the first, but then we have to multiply it by the derivative of r with respect to t. So here's our relationship between our two related rates, that the rate of change of the area is going to be equal to 2 pi r times the rate of change of radius with respect to time. So now we might make our substitution and figure out what's going to happen. The rate of change of that area would be equal to 2 times pi times the radius, and we know that's 60 feet, times the rate of change, which is going at 2 feet per second. And so in this case, our rate of change in area is going to be in square feet per second, and we're going to find 2 times 60, which is 120, times 2 again, that's 240, times pi, and we're going to say that's in square feet per second. And if we were really interested, we could go ahead and use our calculator and multiply 240 times the number pi and get whatever that actual value is. But for our purposes, that's great. That's what we wanted.